Hello everyone, welcome back to the channel. In this video we're going to take a look at one way that we can take percent distortion measurements without the use of a distortion analyzer. Some time ago, about a year ago now, did a video on an HP334A distortion analyzer. We looked at the internals, we analyzed how the circuit worked, and then we did some repairs to get that analyzer working. And since then, I've been kind of fixated with distortion analyzers and trying to build signal sources with high quality, high purity sine waves. And that's led me down my current path, which is working on my project as a long-term project that hope to be completing here in the near future, and then we'll take a look at that when it's complete. But for now, we're going to take a look at this. So what this is an active twin T notch filter, and it's based on a design from the web from Dick Moore on the Tronola website. And I've got the article here that I printed out from his website, and it's here. And I'm not going to go into a lot of detail about it. Like I said, this is his article. It's his work. I've simply taken it from the internet, studied it, and then made my own adaptation of his project here. But in his article, he does a very good write-up, very thorough about theory, some background on his project, and then look here quickly at the schematic for how this twin T notch filter works. And what this is a passive twin T notch filter here, followed by a buffer and some feedback. And it's a twin T. We essentially have two T's in parallel is where it kind of gets the twin T name from. There's a T here made of two bridge capacitors and a pillar resistance, and then the second T is two bridge resistors and a pillar capacitance. And the ratios are shown here for the filter network using the frequency response equation here, which is pretty common to these sorts of circuits here. And we can see that as you change these values of resistance and capacitance, we can tune this circuit to notch out various frequencies. And what we do then is, by applying feedback, it allows us to tighten that notch so that we're not attenuating signals that are outside of our desired frequency. So we touched on this in the previous video where I did the repair work on the HP334 distortion analyzer. How if we have our filter, our notch filter, and it's going to have a notch response at some frequency, but that notch is going to be very wide, and it's going to tend to attenuate frequencies that are outside of that notch on as well. And that's not very desirable for a distortion analyzer because we don't want to attenuate the harmonics. We only want to attenuate and remove the fundamental. So the way we do that is you apply feedback to that notch filter that tightens the notch so that we don't attenuate those harmonics, and we only attenuate the fundamental. And we can eliminate the fundamental. We have unaltered, unattenuated harmonics that then we can measure and sum and get a value of distortion for that signal. And that's what this circuit here is doing. We'll notch out a signal with our twin T filter notch, and then we'll use feedback to tighten that notch so that we don't attenuate the other signals that we want to measure, i.e. we don't attenuate the harmonic signals that we want to measure. And that's what this article here is going to talk about. And he talks about how his response and his construction details and then his measurements. And I'm not going to go into much more than that, just to know that if you want to do some further reading, you can go to the More page on the Tronola website and you can read this article there. So this is my build of his project here. I'll try to get that centered onto the camera, and we can see that essentially this is what he's got laid out. We've got our input signal here. We've got a switch that allows us to filter or bypass, which this is important when you're trying to null the signal there. You'll need to get an initial reference level, and we'll talk about that in a little bit as we actually put this into practice and do some demonstration on how we can use this active twin T notch filter to take a reasonable good measurement of distortion just using this and either a spectrum analyzer or an RMS voltmeter. Put our output signal here, and then we've got our tuning controls here. This is an on. This is my power switch. I've incorporated that into, as you can see here, got off 0 dB and plus 20 dB. One thing not shown on the schematic, but in Dick Moore's project, is he actually included, and I included in this build too, a 20 dB gain stage at the output there, and that's switchable, and that allows you to take some measurements of really low level signals if you need some more amplification. Of course, when you're taking your measurements, if you're going to use the gain stage, you have to factor that in to your measurement and then take that, subtract that mathematically back out of your calculation when you're doing your measurement calculations. We got that. Our frequency range switch down here. This unit covers 20 hertz to 20 kilohertz. And then we've got our coarse and medium tune switches here, and then our fine tune potentiometers here. Take a look at the construction here. We see this is unit's battery powered. That helps me to eliminate any kind of noise that might be coming in off the line there. And those noise levels you want really low for taking very precise low-level measurements there. Any kind of noise and hum coming off the power line, that's going to be it's going to be mixed in with the signal you're trying to measure, and it's going to give you erroneous readings as far as you're going to have introduced interference and distortion into what you're measuring that may, in reality, may not be there. But as we can see here, other than that, the construction is pretty simple. The most complex thing is wiring the switches. We've got two 23 position switches for tuning the coarse and fine tuning. As you can see, there's a lot of resistors there that have to go onto those tuning switches here. Our frequency range switch here, and I've used polystyrene capacitors for the pillar and the bridge capacitors there, and then film capacitors also for the lowest range. And then of course this is our op amps for feedbacks. These op amps are OP. One of them is an OP 2134, OPA 2134, and the other one is an OPA. I believe it's an OPA 134. So they're low distortion, low noise FET op amps. They're if you are in the sort of into the realm of audio performance, these are fairly high performance op amps. I wouldn't say they're definitely the best, but they're the ones that I've used for this project. And there's also the ones that Dick Moore used in his project, so I used those as well. Although when he built his project, I think he used 3 single op amp units here, and I opted to use a dual op amp for the bridge and feedback, and then a single op amp for the gain stage at the end. Just a couple more adjustments here for balancing the pillar trim and the bridge balance potentiometers down here at the bottom. This is to just basically the better that you can get these values balanced, the better your tuning is going to be. So these are really to, once you complete and build, you can adjust these to get the resistances the same for both bridges and the pillar of your twin T, and that's what these potentiometers are here for. Other than that, pretty simple build here. Power switch and the gain op amp selection, and then our fine tune potentiometers, which these are 10-turn wire wound potentiometers there. So let's take a look at the active twin T notch filter in operation here. So what I've done is I've got a signal source hooked up to the input of the active twin T notch filter, and that's coming from my HP 209A oscillator, and it's set for an output of 2 kilohertz. And I've got the fundamental selected here. It's the peak here, and we'll set that reference level to the top of the scale there. We see that we've got a level of about 10.3 dB. And right now I'm in bypass, so we're not filtering the signal. And we can see that we've got two harmonics here. We've got our harmonic here at minus about 55 dB, and we've got a harmonic here, a third harmonic there also. So this is a fairly fairly non this source, it claims to be a low distortion source, and I guess it is pretty low comparatively. Certainly not low by some of the other sources that we may look at later on. But let's look at how this twin T notch is going to work. So I'll put the unit in filter, and what we're going to look at is the response of the fundamental there. We see we dropped the fundamental level quite a bit, and if we put a display line, I'll just set a reference there so we can see that as we switch the filter in and out, we're able to knock that fundamental down quite a bit, but we're not really having an effect on those harmonics, and that's what we're looking for with the active twin T notch filter. So we want a sharp enough notch so that we're not affecting the harmonics, the second and third and so on harmonics, but we need to eliminate that fundamental, because that'll let us use a wider, have more dynamic range on our spectrum analyzer. Now this is already tuned. This filter is already tuned for 2 kilohertz, as I was using it earlier. So I will detune it here, and we can see the tuning process here. So as we start to tune our twin T notch filter, you see that we get some response there on the fundamental, and we can kind of look and see where we need to put our coarse and medium range tuning. And I'm going to raise the resolution bandwidth up here so we get a little bit faster response on this spectrum analyzer. What we can see as we do the coarse and medium tuning, we can see how it responds. What we're looking for here is we're looking for the lowest we can get on our switches, and once we get that, then we can start making the fine-tuning adjustments. And I'm just going to go back and forth between the two. I'll make some adjustments on one bridge, and then I'll come and do the other one, sort of back and forth. If you just do one, if you just focus on one of the adjustments at a time, what you'll find is you'll tend to get your pots, your adjustment, your fine-tuned pots will be at the full travel stop, and you're going to run out of adjustment range. So going back and forth there can really sort of get that. We can really, if we sit and really tweak on them, we can really get that fundamental really out of the picture. There, and there we go. So now that we've got that fundamental out, and we can take that distortion measurement, and we see that our harmonics are there. And what that does is that's going to allow us to downrange on the spectrum analyzer here, and we can really bring those harmonics into view. And it's not as dramatic with this source because, like I said, this is a fairly harmonic rich source. But when we look at some other sources here, this becomes more important, is because as those harmonic levels are lower and lower, meaning that your signal source is more pure harmonically, we really need to remove that fundamental so that we can downrange on the spectrum analyzer to bring those second and third harmonics into the range of being measurable, get them out of that noise floor. You know, if we look at our noise levels here, you know, we're somewhere down minus 70, minus 80 dB. All right, so what we can do now is once we have these values for our second and third harmonics, is we can calculate a value for harmonic distortion. And the way we do that is we know where we start. We've got a value here for our fundamental of 10.2 dB. So that's going to be our starting point. And then we're simply going to take a measurement of our second and third harmonic levels. So we see our second harmonic somewhere about minus 64 dB. And our third harmonic is pretty close there, a little bit lower, about minus, we'll say it's a minus 67 dB. We said that our second and third harmonic levels here were minus 64, minus 67 dB. And we'll convert that to a decimal value, and then we will sum them together. We get 6 e to the minus 7. We'll take the square root of that, which is 7.75 e to the minus 4, and then we'll multiply that by 100%, and we come out with a distortion percentage of 0.077%. So that's essentially measuring the harmonic distortion from a spectrum analyzer. Now what we can do is, because I have the equipment, is we can put that signal into a distortion analyzer, and we'll see how close to this value we can come using the distortion analyzer to calculate the percent distortion of our signal. So what we see here on the HP334A now is taking a distortion reading. I'm looking at the same signal coming in from the HP209A oscillator, and we'll see that we're on the 0.1% range. So this scale here is 0.1, and we're looking at it's about a 0.082%. So where we calculated harmonic distortion and a value of 0.077%, we're measuring a total harmonic distortion of 0.082%. And now this is also going to include noise. One thing that our calculation here is not including is noise. So this is simply a calculation of percent distortion due to harmonics only. This meter is going to also respond to any noise levels and any residual of the fundamental signal here. So it makes sense that it would read slightly higher, but we can clearly see that we can get pretty accurate distortion measurement there, 0.077 being right here. So that's well within our what is a pretty reasonable sanity check there for our percent distortion measurement. All right, so that's all well and good, and we can take a distortion measurement, harmonic distortion measurement using a spectrum analyzer, and we could really do that in this case without even using the twin T notch filter. But let's say we don't have a spectrum analyzer. Can we still use this to take a relatively reasonable, accurate distortion measurement? And the answer is yes, we can. So let's have a look at that now. So I've still got the same signal source, the HP209A oscillator, hooked to the input of the active twin T notch filter. And this time I've got the output of the notch filter going into my RMS voltmeter here. So let's look at how we're going to take this reading. So I've got the unit in, I've got the filter unit in bypass right now, so we're not doing any filtering. And I'll go ahead and detune it here. That'll make this a little more interesting if it doesn't go straight into being tuned. So the first thing we need to do is we need to set, just like on the spectrum analyzer, we need to set our reference level. And I'm going to set it for the 0 point right there. So we're going to use the dB scale on this RMS voltmeter. And I'm going to set that for 0. And so what we're looking at here, so we're on the plus 10 dB range. So this 0 here indicates a plus, is showing what we have is a plus 10 dB level, signal level there going into the RMS voltmeter. I will put the active twin T notch filter into filter mode now, and we'll start to tune it. And what we're looking for is to tune that fundamental until it goes away, and we can tune that signal until to the point where we're unable to get any more null on our signal, and that's when we know at that point that we can take our reading. So now I've gotten the medium and coarse tuning complete. Now I'm starting to do the fine tuning on the using the fine tune potentiometers there, and we can see that as we take that signal level out, it's going to continue to go. It's going to continue to be reduced until we get to a point where we can no longer do any more nullification there. We're getting pretty close to the limits of our ability to, yep. So that's going to be about as much as we can tune it out right there. So let's look at what we've got. So we ended up on the final scale here of minus 50 dB. So this 0 point right here is minus 50 dB. So we're at minus 51, minus 52 dB. Now remember, we started at plus 10 dB on the RMS voltmeter. So we ended up at minus 52, which means we had a total reduction of minus 62 dB of signal level. So what's left here on the RMS voltmeter is any kind of the fundamental that we haven't been able to null, plus any harmonic content and any noise. So really what we're looking at on the RMS voltmeter is a total harmonic distortion plus noise, because the RMS voltmeter will calculate all of those values and sum them all together for us and give us a display. So this may be a little bit closer to what the distortion analyzer showed us for a percent distortion here. But we'll do the same math again, and then we'll take a look at the results. All right, and here are the results of our second calculation here. So like I said, we started at plus 10 dB. We ended up with a total reduction of minus 62 dB in signal level. We can do the math here and see that our calculated percent distortion is 0.079%. So that's closer to what the HP334A was telling us was our total harmonic distortion there, our percent distortion. So still a little bit not quite 82, but you know, we're starting to talk about different responses of instruments and you know, where your instrument's calibrated and whatnot. So again, you know, a little bit closer to what the analyzer said was our value for percent distortion. Now, keep in mind too that when we do this method, you know, with the spectrum analyzer, we were able to analyze the harmonic content of our distortion to see where the various distortions played out, and second harmonic distortion, third harmonic distortion, and so on. In this case, though, we're only being able to see the total, so we don't really know which component is supplying. So if we really wanted to analyze a source to see, is it from second harmonic or third harmonic, we'd really need to use a spectrum analyzer for that. In this case, we're using the RMS voltmeter. We get a value of total harmonic distortion and plus noise there. Again, depending on what you want to look at, different methods for calculating that those values and determining which components are in play and which ones are not affecting it that much. And too, when you're doing this sort of measurement like this with this equipment, you got to keep the limitations of your equipment in mind. We're looking at this RMS voltmeter. It's only going to have a range of down to minus 60 dB here. So depending on where you start, you're only going to be able to go so far with it. So you're only going to be able to take measurements to a certain level. You're certainly not going to be able to get the really super low down into the minus 80, 90, minus 100 dB levels of distortion that you might see for your sort of a higher grade signal sources. You're not going to be able to see those levels with this setup. But this is certainly more than adequate for taking normal distortion level readings with some equipment that may be more accessible than some of the things like your spectrum analyzers and whatnot. All right, so now that we've seen sort of how this active twin T notch filter is working, let's do a demonstration on what we can really use it for, and that's for measuring the harmonic levels of more spectrally pure signal sources. And what we'll do for that is we'll use the signal source from this HP339A distortion measurement set. For those of you who know, this unit has a pretty good signal source here for taking distortion readings. And we'll analyze that and see if we can pick the harmonics out from this source here and look at them on the spectrum analyzer. And I can tell you that just connecting this signal source out to the spectrum analyzer, we're not going to be able to see those distortion products there. This analyzer doesn't have the dynamic range to show us the fundamental plus the distortion products. And we'll have to remove that fundamental in order to see them. But we can, and we'll take a look at those distortion products and see what is contributing to the distortion level of this signal source. All right, so I've got the spectrum analyzer set up now. We're looking at the source output of the HP339, a distortion measurement set. And we're looking at 2 kilohertz again. And I've got the active twin T notch filter in bypass, so we're not filtering anything right now. And we can see that we've got our fundamental here, and our noise floor is somewhere down around minus 60, minus 65, minus 70, minus 75, and we can get that a little better by going to a lower resolution bandwidth here. And if you want to sit here all day and watch it analyze, it'll sweep all the way down to 3 hertz, but we don't have that kind of time. But we can reduce it somewhat, and that'll lower our noise floor a little bit. We can also play around with the video bandwidth, and that'll get us a little bit of less noise in there. But we're not going to be able to pick out. We're not going to be able to pick out our fundamentals just doing this alone. I would expect somewhere around 4 kilohertz we would get a fundamental. We'll be looking for our second fundamental, and it's somewhere down in here. And we can see that we've got some random noise spikes, but these are going to change every sweep. So we're not really those aren't going to be attributed to harmonic distortion, and certainly they're not going to be attributed to the harmonic distortion because they're not harmonics of the fundamental. They will contribute somewhat to noise, or they do contribute to noise, and that will play in for our total harmonic distortion plus noise measurement. But those will vary continuously as the signal varies. We're seeing what's the spectrum analyzer is sweeping, so we're seeing the signal change based on the sweep rate of the spectrum analyzer. But in reality, those signals are constantly changing, and we're just not seeing them. But what we can do is we'll put the we'll go to filter now, and I'm going to raise the resolution bandwidth up so that we get a faster sweep here, because that's going to help us get this tuned here. So now I'm in filter mode, and I'm going to start to tune that fundamental out. And we need to get that fundamental down so that we kind of get it out of the picture. And we got a pretty good jump there. So now we'll just do the fine tuning, and we can really knock that fundamental down. We can see that here we've got it essentially eliminated there. So now that we've got that fundamental out, what that allows us to do is that will allow us to downrange on the input level. And now we can see that our fundamentals coming back. But at the same time, look at what that's doing for our noise floor. So now we're down into the minus 100, minus 105. And if we continue to go down our range, and we'll have to reduce our resolution bandwidth there so we can pick it up. But now we can see clearly, now we've got some harmonics, and these are the harmonics of our fundamental. Now we can pick them out. And the reason we can do that is because we've lowered our fundamental level to a point where we can downrange and see these lower signal levels. So we've got a second harmonic there of minus, it says minus 100. We can see that that's where that signal level is at, minus 101 there for the third harmonic. So we can see from this HP339A distortion measurement set that the source has got second and third harmonic components in it. I don't see anything beyond. I don't see a fourth harmonic. It will be somewhere on in here. All right, so how do we take a distortion measurement off of that? Well, just like we did before. So we need to know where we started at, and we can look at that and see if we come into bypass. We can see that we start off with a value of plus 10 dB for our fundamental. And when we go and put the filter in, and we can downrange until we get our fundamentals back onto the display here. So our second harmonic, we'll say, is at minus, we'll say it's at minus 100. That'll make the math a little bit easier. And we'll say our third harmonic, we'll also say it's at 100, minus 100 dB. So if we started at plus 10 dB and our harmonics are at minus 100 dB, that means our total down for second and third harmonics is minus 110 dB. So let's analyze the math here on this. So we started at plus 10 dB. We said our second harmonic and third harmonics are both at minus 100 dB. That gives us a total reduction of minus 110 dB. So we'll we'll take that and convert that into a decimal number here. We'll multiply by 2 in this case because they're the same. We get 2e to the minus 11. We'll take the square root of that, multiply by 100, and we get 0.00045%. So that is the distortion level, the harmonic distortion from the second and that contributes from the second, third harmonic of our signal source there. So pretty low. Of course, that would go up some if we did a measurement for noise. That's going to come up slightly, but not too much, because we've already factored in the harmonics, and they're the biggest contributor there for the percent distortion. So let's see, just for fun, let's try to take this measurement using the RMS voltmeter and see if we can get anywhere close to minus 110 dB. So just like before, we'll have to set our reference level, and I'm going to do that now. All right, so there is our reference level, and we can already see from our scales here. So if we're starting at plus 10, the most we're going to be able to come down is to minus 70 dB. That's going to put minus 70 here. So we may get another 10, so that's going to put us at minus 80. So really, if we're going to try to take this measurement, we want to start out at a higher range. But I don't believe that the signal source we're not going to be able to get there with this signal source here. So that's not going to work. So we will set our 0 point there, and we'll start, so I'll put this into filter mode, and it's already tuned, so we'll just start downranging here, and when we get to the bottom range, we'll see if we can tune it any more to get any more adjustment there. And it's going to be really touchy down here on these lower scales. All right, so we started out at plus 10 dB for our fundamental, and then we filtered using the active twin T notch filter, and it's very touchy down here at the bottom of the range. So we get we can call that about as low as we're going to get it. So we started at plus 10 dB, and we ended up at minus so that's minus 50 and minus 55 dB. So that is a total signal reduction of minus 65 dB. And of course, we know from the previous measurements that minus 110 dB, that's a little more than half of the total reduction. So we're not going to get we're not going to be able to take a very accurate distortion measurement of this source using this setup. But what we're doing here is we're trying to eliminate the fundamentals so that we can look at the harmonics on a spectrum analyzer here, and that's really what this is useful for here in this case. And that's the part of the reason why I built this unit, so that I can analyze higher quality signal levels and see the harmonic content. Since we already have the analyzer, we can go ahead and take a look at what this HP339 a distortion measurement says is the distortion level of its signal source. We can compare that to what we calculated here based on the spectrum analyzer. All right, so now with just the analyzer set up to measure its own signal source here, we see that for on the 0.01% range, which puts us here at about 0.001, it's about 0.0012% on the meter. And I can tell you from using this instrument, this is about the noise floor here for the distortion analyzer here. So we see that we calculated here for harmonic distortion was 0.00045%, which would put that signal down somewhere about like right there. We're up a little bit higher. Of course, this is going to factor in noise that we've got in the circuit, as this is going to compute total harmonic distortion plus noise. Of course, we've got some of it filtered out here using some of the filtering, but we're not going to filter out anything between 400 hertz and 30 kilohertz there. So again, where we should be right about there based on our calculation, we're a little bit higher. So, it's going to be somewhere in this range here, somewhat higher than what we calculated, because we calculated harmonic distortion only, and we're looking at total harmonic distortion plus noise here. All right, I hope everyone enjoyed the video and was able to pick up something useful from the information here. Again, just some, and as part of our learning process is learning these different things. And, when you build a project, sometimes it tends to lead into other projects. And then in this case, that's what we have here. So I've got this active twin T notch filter, and you can use it to, like I mentioned earlier, I built it primarily to categorize sources as far as harmonic content, and that's important in particular for the current project I'm working on. I wanted to be able to look at the harmonic content of a signal source that's relatively high quality, high purity sine wave, but I need to be able to look at those harmonics and to see what harmonic content's there, so that I can make improvements and work on that to try to get those levels further eliminated. And I think I've done a pretty good job with that so far. But I will be finishing up that project, and then we'll look at that in a future video. But that's all for now. I hope everyone, if you find this interesting or useful, take a look at the Tronola website, Dick Moore's website there, and take a look at his projects. He's got other he has lots of projects on his website other than just this one. But anyway, I'd recommend you check it out, and there's lots of good information there as well. But that is all for now. Thank you for watching.